Hey everyone, welcome back to the Build Hub stage. Next up, we have the co-founders of Monad Foundation, Keone and Eunice. They're going to give an exciting conversation on the architecture and performance of Monad, as well as talking about Layer 1 innovations. Please come up to the stage. I'm going to hand the mic over to you guys. Here you go.
Thank you, Jane. Good morning, ETHDenver, and good morning to everyone who's joining us on the live stream. We're super excited to be here today and to tell you a little bit more about some of the new innovations and features of the recent testnet launch of the Monad blockchain. So, without further ado, we're first going to see an actual live view of the network right now. Keone, can you give this a quick refresh? I see. Now we've switched over to the live view here. And actually, if you want to follow along, you can. You can go ahead and navigate to gmonads.com. You can see that in the upper left corner, gmonads.com. So what you can see here is the fully distributed network. Right now, there are 57 validators distributed throughout the entire world, with the expectation of having over 100 by the time mainnet is launched. Other stats to include here. It's a 500 millisecond block time and 1 second for finality. There is 150 million gas per block, which translates to 300 million gas per second. The expectation is that that also increases up to 1 billion gas per second by the time mainnet launches as well. So, feel free to follow along here. We're going to do something fun and check back in with the live site in just a moment. But firstly, we want to go through a quick exercise of actually pushing the limits of that 300 million gas per second. So what we have here is a slightly modified version of the standard Foundry smart contract. What it usually comes with is the increment function. What we've done here is added a few additional functions that are just really not performant, because why would someone necessarily need to count one by one by one by one, a really big number? Well, we're going to try that. We're going to waste a little bit of gas on the network and see how that pans out. We're going to first zoom in to increment many here. Sorry. My bad. I should have explained a little bit more. Yeah. First, zoom into increment many here, which will pass into this function a ridiculously large number for the contract to increment from 0 all the way to this really large number. Inefficient? Yes. What else is inefficient? Well, we have push many here, which is pushing. Which is adding to an array. It's extremely memory inefficient. And again, if we pass it a really big number, it's expanding the size of this array. Not great. I wouldn't recommend it for your normal standard development practices. But we're going to do it for the case of, again, pushing the bounds of this 300 million gas per second. All right.
Cool. So, yeah, what we're showing here is actually a very inefficient smart contract, but the goal is just to demonstrate the really high gas capabilities of Monad. So we have a very simple demo that calls that counter.sol, calling increment many with an input of 400,000. This costs 141 million gas, and as you can see from the screenshot here, this landed in the next block and then ended up taking about 1 second from start to finish. There's a link to the Explorer, which I think I'll actually take the liberty of going to. Oh, maybe not. Okay, well, let's do this live, actually. Okay, so this is, again, a very simple demo. This code is live. We'll share the link to the GitHub repo so you can try it yourself. But yeah, this is basically just calling that increment many function with an input of 400,000. Gas needed 141 million, and it landed, it looks like a couple of blocks later, and it took a total of 3 seconds from start to finish to do that loop. And then we can actually check it out on the Explorer. And yeah, you can see that this transaction, it's super inefficient, 141 million gas landing in that block and utilizing most of the capacity of that block. We'll do the same thing with push many that Eunice introduced in a second. This is a very expensive call because it's allocating storage. For those of you who are familiar with the EVM gas costs, you know that every slot that is consumed, like every new slot that's consumed, costs 20,000 gas. So it's going to be really expensive to run this with a large input. Here we're allocating 6,500 new storage slots. It ends up taking about 146 million gas, and once again, we'll try that.
So just a reminder, 146 million gas is effectively taking up most of that block space, since each block has capacity of 150 million gas right now.
Sorry, I forgot the name of my input. Yeah, so 146 million lands in that block, and we could check that one out on the Explorer as well, but it'll look pretty similar. All right, so what we showed you was something live, but what we'd really like is for you to be able to try this yourself. So we've put up a really simple demo at monad-speed-test.vercel.app, password Denver 2025. And this is just a simple UI that allows you to submit those kinds of transactions. If you go there, you'll see this, and you'll see you can choose, maybe we'll just do a little audience input actually. So do you want to do increment many or push many? What?
Push many, I'm
hearing.
Push
many, okay, great. And what do you want the input to be? 1,000, okay. And we'll just do like 5 copies of this. Okay, so it landed those 5 transactions, and if we just look at one of them on the Block Explorer, we see a transaction that took up 22 million gas, which is more than the target of 1 full Ethereum block. So it took 22 million gas, and it landed really fast. And you know, the same is true for all these other transactions as well. So yeah, you can play with this yourself. And then the other thing we want to point out is that we've open sourced this repo. It took like an hour to build. It's not like a huge amount of like new code to check out, but you can try it out, and you can try submitting really expensive transactions to the Monad network as well. So github.com/monad-developers/speed-test. And then lastly, you're going to need some testnet tokens in order to chew up a lot of gas. You can use that form link to go ahead and test some, to get some tokens. Oh, yes. I don't think there's a password, actually. Yeah. All right. So the next thing we want to do is do another. Go ahead.
I'll narrate while Keone's handling this.
Sorry, I'm really bad.
We're coordinating with our engineering team live right now to do a real live speed test. We're going to really push the TPS up to some of its capacity. So once that gets going, we should be able to see the TPS start amping up and skyrocketing. If you are on this Block Explorer, one fun fact is that if you click on block time right here, you can actually toggle the parameters a little bit to get a rolling average for how that TPS is calculated, as well as how quickly the TPS is updating on the UI itself. So let's, well, here we see it. The TPS is definitely starting to climb here. So this test here is intended to max out at around, it was supposed to last 10 seconds and max out at around 2,000 transactions per second. I don't think we quite saw that on the screen here, but it definitely did. Oh, well, I guess we're starting to hit slightly larger numbers as well. In any case, this is proof in action. This is literally the network as it exists right now with all of these distributed validators contributing to the network.
All right, so feel free to follow along on your devices on monads.com, and just, all of this you can check out on the Block Explorer as well and dig into what's going on. All of this is live on the live testnet. All right. Next, we want to share just a tiny bit about how this is possible. We're so excited to be sharing with you about Monad and a new really fast EVM that we think will make it a lot easier for developers to build really powerful applications that really scale to hundreds of millions of users and offer really cheap transactions. How do we get that? We get that through a number of different technology optimizations that our team has been working on over the past 3 years. And in particular, we get that through 3 sort of major areas of improvement, which are fast consensus, asynchronous execution, and fast EVM execution. And we're going to talk just a tiny bit about what that means and why we need all of these pieces in order to deliver this really fast EVM with a high-performance distributed consensus. So first of all, with respect to fast consensus, what we want to point out is that from a lot of research that our team has done and investigating different consensus options, we found that hot stuff like protocols with linear communication, that is to say, the leader communicating directly to all the other leaders who then communicate directly back to the next leader, that form of consensus ends up being the most performant and the most able to scale to a large network of validators. In addition, we need efficient block propagation. So specifically in that one-to-many to one story, the one-to-many part is very expensive because that leader is sending a really big block that has a lot of transactions and having to message that directly to all of the other nodes. So we need a really efficient algorithm that allows that leader to send that really big block efficiently to all the other nodes. And we accomplish that through erasure coding as well as implementing a broadcast tree, which we'll talk about in a second here. The second thing to point out is that consensus needs to happen before execution. So we need to move execution out of the hot path of consensus into a separate work stream that's very slightly lagging consensus. And we'll explain why that's really important to unlocking really high performance. And then lastly, and I'm mentioning this because we're probably not going to have time to talk about it in this talk today, but really fast EVM execution on its own comes from having a really performant data store that natively stores the Ethereum Merkle tree data on disk. That combined with really efficient execution that runs many transactions in parallel and could take advantage of the parallel access of this fast data store. So when you stack all these different improvements together, that's how we get that really fast EVM environment that we just demoed to you right before this. All right, so I'll give a real lightning talk about fast consensus. So in Monad BFT, which is the consensus mechanism by which we get fully globally distributed consensus, so we get that amazing map that currently has 57 validators fully globally distributed with the expectation of over 100 at the time of mainnet. This comes from utilizing this fan-out, fan-in approach. So as you can see from this diagram, in this story we have 3 consecutive leaders, Alice, Bob, and Charlie. And the way that a block ends up getting produced in Monad is the leader, Alice, chooses an ordering of transactions and sends that block with all those transactions out to all of the other validators who are shown in blue. And then all of those validators evaluate the validity of that block before sending a vote yes or no to the next validator, Bob. So that's the fan out and fan back in sort of mechanism that's going on there. And then Bob, his job is to his job is actually 2 things, but we'll talk about the first thing first. His job is to aggregate the votes that all those other validators sent into something called a quorum certificate, which is an attestation of the validity of that previous block that Alice produced on the part of all of those other validators. So Bob produces a quorum certificate, which is proof to anyone who can see it that all of those other validators signed off on this block. And then Bob sends the quorum certificate out to everyone else, once again fanning out. And so then at that point, we then land at the point where the second row of blue sort of vertical lines where all the validators are once again, thank you, once again, getting the QC and evaluating and voting on it before sending it to Charlie. And then lastly, Charlie produces a QC about the previous QC, which we call a QC on QC, and messages that out. And then at that point, all of the nodes now know that Alice's block has been accepted by the network and is enshrined. So that was just kind of a high-level summary of how the BFT consensus works. This allows Monad to scale to hundreds of nodes participating directly in consensus as leaders and voters. And then lastly, we get some additional performance by pipelining the QCs together with block proposals. So we've kind of extended the previous image just to include one more validator who we'll call, I think, David. And so there's just one more step here. But what you can see actually is that at every stage of the process, so when Alice produces a block, she sends out that block with a list of transactions. When Bob sends out a QC, he also sends out a new block with a new set of transactions as well. And so every single tick of the consensus, there's a new block that's being produced, and this pipelining increases the overall throughput of the system. Okay, so one other thing we're going to share about really briefly is an algorithm we call RaptorCast. RaptorCast is an efficient mechanism for allowing, in this story, Alice, who's sending out a really big block that has 5,000 or 10,000 transactions in it, and sending that big block out efficiently to all of these other nodes, communicating almost directly. Some really quick math is that if you have a block that has 10,000 transactions in it, and each transaction is 200 bytes, that's going to be a 2 megabyte block. And if you need Alice to send that 2 megabyte chunk to every single validator, multiply that by the number of validators in the network. That's a huge amount of upload bandwidth, which would be really bad because we can't have validators have to have insanely high upload bandwidth. So how do we solve this problem? We solve it through an algorithm called RaptorCast, which basically introduces a 2-level broadcast tree where the block is erasure coded into a bunch of smaller chunks. In erasure coding, you introduce some repetition so that you can take any subset of the chunks that roughly corresponds to the size of the original block and reproduce the block from that. So chunk the block into a bunch of smaller chunks, and then for each chunk, send it through a 2-level broadcast tree where one validator acts as the first hop recipient and then broadcasts to all the other validators in the node. So I like to think of this as like the idea of sending a message, broadcasting a message into the sun, and then having the energy of the sun super broadcast that out to everywhere else in the universe. If you are a sci-fi fan, you might know what I'm talking about here. So we have this broadcast mechanism where we're sending each chunk to one validator in the rest of the network, and then that one validator is responsible for propagating it to everyone else. Lastly, just to note, the weighting of chunks, the assignment of chunks to first hop recipients is weighted by the stake weight. So this produces BFT, this produces Byzantine fault tolerance because as long as supermajority of the network is behaving properly, they'll act as proper first hop recipients and propagate the blocks to the chunks to the rest of the network. All right, so we're just going to, good?
Yeah, I was going to say, I don't think we have enough time to walk through asynchronous execution this time around, as we have 51 seconds left. However, there's a lot of material online already. Actually, a talk from last ETHDenver, among other types of educational material to learn about that.
So thank you so much for having us here. Once again, you can check out monads.com to see the network live. You can check out testnet.monad.xyz to check out a ton of amazing applications that are already on the Monad testnet 1 week in. And you can check out those resources that we shared earlier to try it out yourself. Thank you guys so much. We're excited for fast EVM. Thank you.